You may well have heard of the normal distribution before. You might have seen graphs that resemble this bell-shaped curve at the bottom, and you might have heard people talk about the tail end of a bell curve or some measurement that follows or fits a normal distribution. We're going to investigate exactly what that means, and we'll look at how we can use the normal distribution model to help us make sense of a whole range of different scenarios. Before we dive into that, I'd like you to look carefully at the picture on the left. Take a look at the weights, look at what you can see from it. I'd like you to ask yourself these two questions. What do you notice and what do you wonder? And I'd encourage you to pause the video at this point and write down anything you can to answer either of those two questions. Once you've done that, come back and I'm going to prompt you with a few more questions you might want to ask. So here's a few questions you might care to ask yourself. Why are some weights visibly more worn than others? If you look carefully, you'll see that the paint has been scraped off the weights, the point where you push the pin in. Why do you think this is? Why is there more wear and tear on some than others? Do you notice anything about the pattern or the distribution in general? What is the most commonly lifted weight on this machine? You may not know that for sure, but perhaps you can make an estimate based on what you can see in the picture. And similarly, could you estimate what proportion of users lift between 30 and 90 pounds? Or perhaps give the probability that the next user lifts a 100-pound weight. Now, I can't give you exact answers to these questions, but hopefully you can see from the picture that it might be possible to come up with a reasonable prediction based simply on the amount of wear and tear that we can see here. If people are pushing a pin into the weight that they plan to lift, then we can see straight away the most common weights people tend to lift. We're looking somewhere in the 50 to 60 pound range, perhaps around here. They seem to be the most commonly used because they're the ones that have been worn down the most. And by the same token, up here we have some that are only just slightly worn and others even further above that are barely worn at all. A 15 or 20 pound weight is unlikely to be used apparently. And similarly, any weights beyond about 100 pounds down at the bottom are also fairly uncommon. This ties in with what you can see on the bell curve at the bottom of the slide as well. There are some commonly used weights that perhaps lie within this range, and then there are some less commonly used weights, perhaps right at the tail end up here and at the tail end down here. And yet there seems to be a reasonable amount of symmetry in this particular picture as well. We're seeing that the number of people who lift more than 90 pounds is probably similar to the number of people who lift less than 30 pounds. You might make some kind of estimate about what proportions are involved. It's very hard to see exactly unless you know how to convert the amount of wear and tear into the number of times the pin has been pushed into a hole, but you can probably make a reasonable assumption that the probability of somebody lifting a 100-pound weight based on what we can see on this machine is probably fairly low. I'd say less than 5%, given how much and the frequency of use within the middle range and how much it tapers off towards the end. We're going to look at how we can use the normal distribution to model this more precisely, and then using only two key statistics, the mean and the standard deviation, we'll be able to answer questions like what proportion of users lift between 30 and 90 pounds, what's the probability that the next user lifts 100 pounds, and so on and so forth. So let's start by recapping what we mean by a statistical distribution. You've already come across a few. In fact, you've dealt with some since you first started learning about probability. The uniform distribution, as the name suggests, is a probability distribution where the probabilities are all the same, uniform as in all the same. So the classic example will be you roll a dice, you roll a fair six-sided die, and the result will come out looking something like this. You can make a table that represents all the possible outcomes. So that's what the small x tells you there, 1, 2, 3, 4, 5, or 6, that's what you could get. And then underneath, the probability that you actually get that particular score. So there's a 1 in 6 chance of getting a 1 when you roll that dice, and there's a 1 in 6 chance of getting a 2, and so on. This is what the graph would look like. Very boring. Every single bar on the bar graph is the same height, each of them coming out at about 16%. 1 in 6, if you want to be precise. This one is known as the uniform distribution, and if you want to find a formula that describes the probability for something like this, then you can. With a weighted dice, you might need to write down the probability for every single number, but for a uniform distribution like this, you can generalize. Say the probability that the score we get on the dice exactly matches any particular value is just 1 over n, where n is the total number of numbers on the dice. In this case, 1 over 6. So there's no need to perform a separate calculation to find the probability of getting a 4, or the probability of getting a 5, or the probability of getting a 2. They all give the same answer, in this case 1 over 6. Here's a slightly different situation. Coin flipper. If you toss 4 coins and you count how many tails you get, then it turns out you don't get a uniform distribution. You might get no tails at all, 1 tail, 2 tails, 3 tails, or 4 tails. But some of those outcomes are more likely than others. The probability of getting 4 tails is 1 in 16 because you would need to get tails for the first coin, and there's only a 50% chance that happens, tails for the second, tails for the third, tails for the fourth. Each one is another 50% chance. So the probability of all 4 coming up tails is a half times a half times a half times a half. However, getting 3 tails and 1 head can happen in 4 different ways. Could happen like what we can see here, where the first coin that gets thrown comes out with heads, or it might be the second coin that gives you heads and the other 3 give tails, or perhaps the third or the fourth. That gives 4 different ways to get 3 tails and a head. And similarly, symmetrically, there are 4 ways to get 3 heads and a tail. And there are actually 6 different ways that you can get 2 of each. It could be the first and second, the first and third, the first and fourth, the second and third, the second and fourth, or the third and fourth. Now those numbers, 1, 4, 6, 4, 1, you might recognize from Pascal's triangle. They give us a nice little symmetrical graph again here, but you can see that the values near the middle tend to be more popular. So if you're betting on how many tails are going to come up, then you should be betting on 2 tails when you toss a coin 4 times. It's not just that on average it works out as half the number of coins, but it's more like there are lots more ways in which you can get 2 tails and 2 heads than there are ways in which you can get 3 of one and 1 of the other, or 4 of all the same. This one is known as the binomial distribution, which hopefully you remember. The binomial distribution also has a formula, but it looks a bit more complicated. So in this case, I've got n choose r times p to the r times 1 minus p to the power of n minus r. And the r is usually used in this case, but just for the record, x and r in this case would be the same. So you could replace r with x if you like, or you could write probability that x equals r equals n choose r, p to the r, 1 minus p to the n minus r. It essentially combines 3 different things. The probability of success a certain number of times, that's p to the power r. The probability of failure a certain number of times, that's the 1 minus p to the power of n minus r. However many coin tosses didn't come up tails, that's the number of times you need a failure to occur. And then the n choose r is the binomial coefficient. It's the number of different ways that particular outcome could happen. Now, both of these are examples of discrete random variables. They're called variables because the number varies. The number you get when you toss a dice could be anything from 1 to 6. So there's variability built into that. But also they vary randomly. So you can't predict what the dice throw is going to give you. And similarly, you can't predict how many tails you'll get if you toss 4 coins. However, the variables that vary randomly are discrete variables. That means there are only certain values that are possible. When you toss a coin 4 times and count the number of tails, you can only ever get 0, 1, 2, 3, or 4 tails. If you roll a 6-sided dice, there are only 6 possible outcomes, 1, 2, 3, 4, 5, or 6. What we're going to be looking at with the normal distribution is something called a continuous random variable, where instead of the possibilities being restricted to certain values, we'll have more like a sliding scale, or rather than a counting of something, like with the coin flipper, we might have the measurement of something. Just like when we look at the distinction between discrete data and continuous data. Notice here that the capital X, this is a little bit of a sneaky idea, but capital X is different to lowercase x in this context. The lowercase x is like a particular example of what you might get. So lowercase x could be 5. You might be saying, what's the probability that capital X equals 5? But the capital X itself is more like a representation of the experiment itself. If you are to roll a dice, what would you get? And there's no answer to that question. You can't say what would you get if you roll a dice, because the answer is, well, I don't know, it could be a 3. It might not be. It might be something else. But we want to be able to describe, if we can't say what capital X will be, we can at least say things about it. We can talk about the probability of it being a particular value. So one way that I find helpful to think of capital X is the outcome of the next experiment. If I'm going to carry out another experiment, if I'm going to toss a coin 4 times and count the number of tails, then capital X will represent in my head how many tails I am going to get. And of course, I don't know how many tails I'm going to get, but I can tell you with confidence that the probability that it's going to be 2 tails is 6 out of 16. So I could write the probability that capital X equals 2 equals 6 over 16. Or if I'm throwing a dice, I can say capital X represents the number that I'll see on the dice when I next throw it. And I don't know what that number is, but it could be one of 6 different possibilities. And I know the probability of it being any one of those things. Another way to think of it is representing the outcome of all possible experiments. So it's not something we can tie down and say it is this value or it is this value. But what we can do is talk about the probability of it taking a certain value. We can also generalize and say what's the probability that it's less than or equal to a certain number. If I toss a coin 50 times, what's the chance that I'll get between 40 and 20 tails, for instance? We can put bounds on it and talk about a range of possible values. And we'll do a similar thing when we get to the normal distribution in a moment. But it's important to remember that capital X doesn't represent some particular number that we just need to calculate. It's more like it represents the outcome of performing this random experiment again, and all we can say with any certainty about it is the probability of it taking certain values or being within a particular range. So the normal distribution is a way of modeling the behavior of a continuous random variable. Good example here would be the height of a person, or the length of a hamster, the weight of a randomly chosen newborn baby, or the speed of a randomly chosen horse. We're thinking of this in a sense like throwing a dice or tossing a coin a bunch of times. There is an element of randomness built into this, so that if you are to select a member from a population, then there should be something you can measure about that, and it's the measurement itself that we're interested in making probability statements about. This is a good way to start to make sense of the difference between continuous random variables and discrete random variables. So I want you to pause the video and have a think about this question. What is the probability that a randomly chosen person would be exactly 1.7 meters tall? Now, I'm not talking about approximately 1.7. I'm not saying to the nearest centimeter. I'm saying exactly 1.7. Have a think, pause the video. When you think you've got a number, an actual probability, then unpause and we'll see if we agree. Okay, the tricky thing here is that this is the kind of question that you would never really ask about somebody's height. We don't say who here is 15 years old, and then when someone says, oh yeah, I'm 15, you say, hold on a second, your birthday was 3 days ago. You're not 15, you're 15 years and 3 days old. When we talk about age, we're assuming that people are truncating their age. They don't quite round in the traditional way, but they will round down to the largest whole number that's no bigger than their age. But the chance of you meeting someone who has been alive for exactly 15 years, well, that seems pretty slim all of a sudden. You'd have to meet that person at exactly the moment, which is 15 years in the future from the moment they were born. It's the same with this. Exactly 1.7 meters tall? Well, basically 0. And it's not just roughly 0, it's exactly 0. The reason for that is that we're not dealing with a finite number of possibilities. We are dealing with an infinite number of possibilities. We're no longer saying how likely is it that you roll this particular number on a many-sided dice. We're saying how likely is it that your height is exactly 1.7 meters when it could have been any number within a range. Even if that range is fairly small, even if you could say that nobody is going to be taller than 2.5 meters and nobody's going to be shorter than 1 meter, even if you could say that, well, you've still got an infinite number of possibilities within that range. Even if you know that someone is between 1.6 and 1.8 meters, the chance of them being exactly 1.7 is still 0, because there's only one number that's exactly 1.7, and there's an infinite number of numbers within any given continuous range. So if the answer to the question is so nonsensical, then something is wrong with the question. Something about what we're asking doesn't make sense. We shouldn't be asking whether a person is exactly 1.7 meters tall, because it doesn't really make much sense to ask that question. What about, what is the probability that a random person is 1.7 meters tall to the nearest centimeter? And that's probably what you would naturally assume somebody means. If they say, are you 1.7 meters tall? Then you would assume there's some kind of range within which you would say, yes, close enough, we'll go with that. And in this case, that's equivalent to saying, what is the probability that your height falls within this continuous range between a lower bound of 1.695 and an upper bound of 1.705? And that's something you could actually put a number onto. It's worth thinking about this idea of probability of 0 and the idea of something being impossible. Previously, you've been told, possibly even by an A-level maths teacher, I've told people in the past, I've taught this, that a probability of 0 means something is impossible. And generally speaking, in the contexts in which we say that, it is true, but the context is often discrete random variables. We're talking about the probability of getting a 7 when you roll a 6-sided dice. There are no ways to get a 7, and there are 6 different possibilities. 0 out of 6, 0. And that is impossible. But there's a difference between that and, let's say, I pick a number between 0 and 1. Could be any number, 0.732249845, or whatever it might be. But it's a number that could be literally anything between 0 and 1. And then you have to guess that number. Well, now there's only one number that's the correct number, but there's an infinite number of possible numbers that could be my mystery number. So it's not quite the same as saying 0 out of something finite. We're now trying to find one correct value out of an infinite number of possible values. And that still kind of gives 0. There's no other number that we can put on that, but it's a different kind of 0 in a sense. It's the 0 you get when you try dividing by infinity. So it's a strange one, but it's not the same as something being impossible, because it is possible to be exactly 1.7 meters tall. It must be, because well, I'm taller than 1.7 meters. And at some point I was shorter than 1.7 meters. So somewhere in between, I must have been exactly 1.7 meters at least once in my life between those 2 points. So it happens, but I suppose you could argue it might happen for a brief instant of time, a moment in time when you happen to be exactly 1.7. And the likelihood of finding someone ever who's exactly any given height is still 0, even though people are particular heights at different times. It's a little bit of a strange one. So generally speaking, if we're dealing with continuous random variables, it doesn't make any sense to ask what's the probability that this equals something. The only way we get meaningful answers is if we ask questions involving a probability range. We could ask, how likely is it that this person is shorter than such and such? Or how likely is it that this person's height is between this and this? Incidentally, we can use the normal distribution calculation model that we're going to talk through shortly to estimate things like the probability of someone being roughly 1.7 meters tall. There's a 3% chance that an adult male will have a height that rounds to 1.7 meters, to the nearest centimeter. Incidentally, there's about a 5% chance that you'll be within half a centimeter of the mean height, which is 178 centimeters. This is based off data for adult males in the United States. So it may be slightly different depending on your population and gender. Now we're going to look at the mathematical basis behind the shape that we recognize as the normal distribution curve. It's also known as a bell curve because it looks vaguely like a bell, or the Gaussian distribution, named after the same mathematician Carl Gauss, who you might have come across when learning about arithmetic series. Now, the mathematical formula for this graph looks something like y equals e to the minus x squared, with a few graph transformations thrown in for good measure. Now, you'll be grateful to hear that you don't need to memorize this formula. No one's going to ask you what it is, but I think it's interesting briefly to look at it and think about what will happen for large or small values of x. So if x is equal to 0, you'll have e to the power of 0, which just gives a 1. So the height of the graph will be just 1 over root 2 pi times 1. But as x gets bigger and bigger, e to the minus x squared over 2 will get smaller and smaller. It's exponential decay. But if x is a negative number, when you square it, you still get a positive result. So it's still exponential decay even as x becomes more and more negative. And that's why this graph seems to tend down towards asymptotes at y equals 0, both for positive values of x and for negative values of x. The other really interesting thing about this, and the reason it's been scaled down in the way that it has, been stretched by scale factor 1 over root 2 pi in the y direction, if you like, is that this graph now has an area of 1 underneath it. Even though technically the curve goes on forever in both directions, it gets so close to the x-axis so quickly that just like with a geometric series that has a small enough common ratio, you can calculate the total area of this shape, which is technically of infinite width. Because the height gets small so quickly, the total area is 1. It never goes above 1. And that 1 is going to be really important for us because that is going to relate to the probability of certain events taking place. Essentially, the area under the curve tells you the probability that your continuous random variable will take certain values. And this ties in nicely with what we were saying about it being impossible to say what's the probability that our continuous random variable is equal to something. The area enclosed under the graph between, let's say, x equals 1 and x equals 1 is 0. There is no area if you've just got a single line. You have to have a range. You've got to go between two different values to get any kind of non-zero area at all. So if you've got a range of values, you could think about the lower bound and the upper bound for your two values, calculate the area in between, and hey presto, you've got the probability that your continuous random variable takes a value within that range. This is more commonly what the normal distribution curve will look like. Just by messing with the scaling on the x and y axes, you can make any normal distribution curve look like this. So this is generally what I will sketch when I'm in the middle of a normal distribution question. I draw a quick diagram here, and I mark on the key features so that I can check that my answers make sense. It's going to be particularly useful when we're looking at working backwards with a normal distribution curve, when you already know a probability and you're trying to work backwards to find the values. But we're going to start by doing the forwards direction, and we need to understand a few important features of the curve before we start calculating with it. The first thing you want to notice is that it is perfectly symmetrical. You can kind of see that from the mathematical formula, the fact that you've got an x squared in there we've talked about, but the curve is perfectly symmetrical, meaning it's exactly the same above the peak as it is below the peak. That means that the area to the left and the area to the right of that middle point, the highest point, they're exactly the same area. And since the total area is 1, the area on each side of the middle line must be 0.5. Now I'm writing them as percentages in here because they represent probabilities, so it's often helpful to think in terms of percentages. It helps us usually to have a slightly clearer intuitive sense of what's going on. There is also a point of inflection. This, mathematically speaking, point of inflection refers to the moment when the curve stops getting steeper and starts getting less steep, or maybe stops getting less steep and starts getting more steep. In this case, as you move along from the middle line, from the midpoint towards the right, you find that the curve starts out with a 0 gradient at the top, but then the gradient becomes more and more negative up until a certain point. And at that point, the gradient won't get any more negative. It's got as steeply negative as it's ever going to get. And at that point, it changes the direction of the gradient change, if you like. It's a bit of a subtle one. It's a more subtle point than a stationary point. We can see what stationary points look like. They're often maximum or minimum points, or they may be a stationary point of inflection, like the wiggle that you get in the middle of a y equals x cubed graph. But this is a non-stationary point of inflection. The curve stops being rounded up and over, if you like, and starts being rounded down and in. So the middle section of this graph curves in such a way because the gradient is decreasing throughout the middle. Whereas beyond that point of inflection, as you move to the right, the gradient is now increasing again. So it starts at 0, and as you move along, maybe it gets as steep as, I don't know, on this diagram with this scale, kind of looks like it's got to a steepness of maybe -2. But then the steepness starts to increase again from -2, maybe -1.5, -1, -0.5, approaching 0 again as the curve moves to the right. That point of inflection is where the gradient changes from decreasing to increasing. And there's another one on this side. The gradient is increasing up to the point of inflection, and then it starts to decrease after the point of inflection there. The mean is the center of this distribution. For a perfectly symmetrical distribution, the mean and the median are the same place, but the key statistic that we use when we're dealing with the normal distribution is the mean itself. We give it the value mu, and it sits right in the middle here. Not only that, but we can identify those points of inflection that we talked about by using the standard deviation. The mean plus the standard deviation gives us this point on the curve where the curve starts to change its gradient change. It's the moment when the gradient stops increasing and starts decreasing, or vice versa. It's a change in concavity is another way to call that. And if you split further, you can see that the 50% that we had above the mean can be broken into a couple of chunks. There's a 34-ish% chunk between the mean and the mean plus the standard deviation, and then the remaining 16-ish%, it's more like 15.7, but roughly speaking, this is a good rule of thumb. 16% lies more than one standard deviation above the mean, and there'll be an equivalent 16% that lies more than one standard deviation below the mean. So, for instance, if you have a mean score on an assessment of 100 marks and the standard deviation is 20 marks, you would expect 16 people to get at least 120. 16% of people, and you'd expect 16% of people to get a score as low as or below 80. And you'd expect the other 68% of people to get somewhere between 80 and 120. That's how this works. And if you have a continuous random variable that can be modeled by a normal distribution, if you know the mean and you know the standard deviation, then you can say with a high degree of confidence what proportions you would expect to lie in different sections. We've also mentioned how the curve is asymptotic. So as you move further and further from the mean, either above or below, the probability of being within any given range will shrink smaller and smaller. So that although theoretically you could go as far as you like, in reality you end up getting numbers that are so close to 0% that it's incredibly unlikely that you would ever get an example where this actually happens. Be like saying, what's the probability of finding a hamster that weighs more than a kilogram? It's very, very unlikely, because maybe the average weight of a hamster is 100 grams or something. And although the standard deviation might be 20 grams, 30 grams, you're not going to get very many standard deviations away from the mean before the probability of being in a position like that drops so low that it's never actually going to happen in practice. Here's a few key points that are worth remembering. They're good rule of thumb. The most important one is already demonstrated for you up there on the diagram, this 68% within one standard deviation of the mean idea. But more simply than that, the first thing that you want to get your head around is that 50% of the values lie above the mean and 50% lie below the mean. Remember, 0% of them lie exactly on the mean, because it's an exactly something. The probability of being exactly anything is 0, but the probability of being above the mean is 50% and below 50%, which is equivalent to saying the mean and the median are the same. Roughly speaking, 68% of values lie within one standard deviation of the mean. So if you know the average height of people and you know the standard deviation of people's heights, then you could confidently state that about 68% of people are within a particular range, whatever the mean is, give or take the standard deviation. If you go further afield, if you jump to 2 standard deviations above and 2 standard deviations below the mean, you're now encompassing about 95% of the population. So somewhere in between those two, somewhere between 1 standard deviation and 2 standard deviations, is where you would find the quartiles. You remember that the, before 1 standard deviation, the upper and lower quartiles contain the middle 50% of the data, which means it's going to be something like 0.7 standard deviations above and 0.7 standard deviations below the mean. That would correspond to the upper quartile and the lower quartile, so that you've got 25% above and 25% below at each end. But you can see that we've got 68% within 1 standard deviation, which is pretty much 2/3 of the population, increasing to 95% within 2 standard deviations. So you're casting your net a bit further afield now and saying, well, we're going to be more flexible. We're going to allow values that are surprisingly high and values that are surprisingly low, but still not so high and so low that you'd be gobsmacked to discover something outside that range. In fact, within a class of 20 students, you would expect that nearly all of them would lie within 2 standard deviations of the mean for whatever it was you happen to be measuring, but you'd probably find that one of them was either surprisingly tall or surprisingly short compared to the average, or maybe they are surprisingly good at holding their breath or surprisingly bad at holding their breath. Whatever it was you were measuring that was modeled by a normal distribution, you'd find that 5% of the values fall outside this range. But if you spread your net even further to within 3 standard deviations of the mean, then you're going to pick up all but 0.3% of the population. So yes, there will still be that handful who are at the extreme end, one way or the other. I once shared a cabin with a chap who was 6'8", which is definitely at the tail end of that distribution for height. You will meet people who are particularly tall or particularly short or particularly good at solving IQ problems and particularly poor at solving IQ problems. Whatever it might be, there'll be people at each end of the spectrum, but within that 3 standard deviation range, you'll find 99.7% of the population. We can move this curve around by changing the mean. Basically, that means if you think about the normal distribution curve on a set of axes, you can translate it horizontally, and you can also stretch it or squash it by changing the standard deviation. In fact, when you change the standard deviation, it both stretches it horizontally but also squashes it vertically to preserve the property that the area underneath will be exactly 1. So that's always going to be preserved, but it means you can basically have a normal distribution curve that fits your own specific situation. It doesn't have to have a mean of 0 and a standard deviation of 1 like the picture at the top. We can modify it to get the standard deviation, the normal distribution that fits the mean and the standard deviation for our own particular situation.